This is the 4-2 notes for Calculus 1. We are going to be covering two important theorems in this section, so let's get right into it. Theorem 4.8 from your textbook. It's called Rolle's theorem. It says, let a function be continuous on a closed interval AB and differentiable on an open interval AB with f of a equals to f of b. Therefore, there is at least one point C in that same open interval such that the derivative is equal to 0. Okay, so as with everything, when it comes to reading theorems, it's not always the easiest to decipher what's going on. So I'm just going to just highlight the important keys here. So in order to use Rolle's theorem, what do you need? You need a function that is continuous, and you need a function that's differentiable. Now, there is a key designation here. We are using a closed interval, which means the values are included on both sides when you initially start the problem. When we talk about differentiability, we're dealing with the not including the endpoints. But generally, when we do Rolle's theorem, we're checking to see three things: continuous, differentiable, and this last concept, f of a equals f of b. Well, if you're looking at this problem, look at what a and b are. A and b are actually the endpoints. So what is this saying? This is saying take your endpoints, sub them into your original function, and they have to be the same. Okay, that's the key. So you have to get the same value of y there for this to actually work. The points have to be the same height on the graph. Okay, in every Rolle's theorem type application problem, we are going to check those three things that are highlighted to start the problem. Then, once you have an idea where you say, okay, all three of these check out, then the conclusion is obviously the key to the theorem. So remember, so for this it says there's at least one point C, so just FYI, that's a value of x. So there's at least one point in the interval, and it is going to be the open interval AB. So we're not going to include the endpoints when we're making this decision. There's at least one point such that the derivative, when you sub in that value of x, is going to be 0. Okay, so the best way to really go on with this is to talk more about the picture, right? So let's talk about, so right now we need an interval, right? So interval right here is going to be AB. So note, we have a graph right now that is going from A to B and includes the points A and B. So we know that if we draw this graph, we don't have to pick up my stylus or your pencil or your pen or whatever. You don't have to pick it up, so that means we definitely have continuity. Differentiability is based on continuity and any of those funky cusp, corners, vertical tangent designations, and clearly this is just a simple curve. So it's definitely going to be differentiable. So the key is, what about f of a equals f of b? So does it appear that when you plug a and b into this function that they have the same y values? Well, what they're trying to show you here by this dashed line that's going on, this green dashed line, is that they're on the same horizontal line. It's just an imaginary line, but essentially those values of f and a and f of b are the same. So what does the theorem state? Let me get rid of some of the stuff that I put on here. So what does the theorem state? So if you start here and you move through this curve, if you end up at the same height at the end of the interval, then somewhere on that curve there must be a point C, or x, value of x, where there is a derivative of 0. So, to be clear, what is the derivative? It's the slope of the tangent. So, put this a better way. If you start here and end up here, right? Start here, end up here, on a curve, you have to go usually, up or down and come back again. What they're saying is that eventually you're going to have a tangent line to that curve that has a slope of 0. That's all this theorem states. This is actually another key theorem when it comes to determining critical points and things like that. It's sort of the basis behind all of that. But this is the key to the concept, is that somewhere on the curve there must be at least, so remember they use these terms at least, which means there could be more than one, but there's at least that many that will occur where the derivative will be 0. Okay, so just to summarize in layman's terms, it says the key is understanding why this must occur. Let's take a look. If there is a continuous interval, the graph must curve up and back down again, or vice versa, to return to the same function value. So as explained, if we start, let's say, here, in order to get to here, we must go up and down or down and up in order to get back there again. From what you have learned previously, whenever this happens, a horizontal tangent line occurs at the highest and lowest points. We call those the extrema, as long as the function is differentiable throughout. Okay, so this is important too, is that what if this graph had a cusp or some other weird thing going in on it? It maybe would not have that scenario. So like if I started here and I went up to, let's say, this and down again, there is no tangent line over here, right? So that means it has to be differentiable, or this theorem will not apply. And then, lastly, we all know the horizontal tangent lines have a slope of 0. So basically, in this case, what we just did was we found a critical point and also a maxima for our function. So Rolle's theorem is actually a great way to it's sort of the concepts behind a lot of those theorems that you learned in the last section. Okay, so let's just do an example. It says, now let's apply Rolle's theorem to the function f of x equals x cubed minus x squared minus x on the closed interval -1 to 1. Okay, so if you look at the graph over here, this is the graph of that third degree function polynomial, and it is going from -1 to 1. Note there is extra pieces on the graph. So what they're saying is they want you to basically analyze this from -1 to 1. So what do we need to do? So we're going to find the points for -1 and 1 on the graph, right? So we have to look at this and go, well, what are the requirements for this? Well, first of all, if I were to start at -1 and follow the graph, is there anywhere where we are breaking continuity? No. So therefore, this is continuous. Are there any cusps, corners, weird things going on here? Well, we know there isn't, because this is a polynomial, and polynomials don't have that, which means this is differentiable. So that must be checked. The last thing is are the endpoints function values, are they equivalent? Well, the line on the graph tells you this, that they are clearly both equal to -1, because they both have the same value of that. But note, you're not going to be given the graph most of the time. So what do? Of course, you just take each one of these and just plug into the equation and make sure that you get the same value when you do that. Now note, if you don't get the same value, you can't apply Rolle's theorem and you just move on. So there might be problems in the homework or in the labs where it says something like, can you apply Rolle's theorem? And sometimes you can't. So you have to check that. Don't assume that you're going to be able to do that. So always check these 3 things, and once they're checked, then you can move on. Okay, so it says, since the conditions are satisfied, Rolle's theorem states there exists at least one point on the open interval -1 to 1. Okay, that has a horizontal tangent line with slope 0 running through it. All right, so this should make pretty good sense to most, I would assume. So basically what it's saying is, first of all, remember this is only on the open interval -1 to 1. So we are not including the endpoints, and we'll talk about why in a second. But it's saying somewhere on the green line of thing, there has to be at least one point where there's a horizontal tangent. Now, hopefully all of you are staring at this picture and going, it's going to happen right there. So there's going to be a horizontal tangent that's going to occur approximately right there. So that's what Rolle's theorem basically states. But a sort of a more what you're actually supposed to do in Rolle's theorem is find that value of x. So what are we doing? We're basically doing this. We're going, okay, well, what is that value of x? And in a lot of time in the theorem, they call it the value c. I'm not really strict with that. So just realize you're trying to find whatever value of x is where that occurs. That's what Rolle's theorem is. And just as a side note, what I was saying before, so you can include the endpoints in the same manner that you couldn't do it with local extreme points, because at the endpoint we have no idea what's going on after that, or before that, or after it. So we don't know if there could have been, like, if the line keeps on going and it wouldn't create a horizontal tangent on either side. So just realize that you can't use the endpoints, basically because all this extra stuff, we don't really know what it would do if we don't have a graph in front of us, or what it's going to present as. So we can't use that. So it's always, whenever we apply this, it's always on the open interval. Okay, so just it said, can you locate that in the graph? So obviously, that is here, right? Our little point there. It says, so the only thing left to do is to determine the value of c, so basically x, that has a horizontal tangent line running through it. And just like Rolle's theorem says, we need to find where f prime of x equals 0. Okay, so how do we do that? We have to take the derivative of our function, a lot like we have done before. So what do we get when we do that? We get 3x squared minus 2x minus 1. Okay, we then have to set that equal to 0. So most of you are probably thinking, oh, isn't this what we did to find critical points, critical values? Absolutely. So I do wonder sometimes why this isn't shown before the previous section, but it is what it is. It's basically the same concept. So just remember, if we're factoring this, we know that if the first term is 3x, this has to be 3x and x. If the last term is 1, these both have to be 1s. This is a very easy trinomial factoring problem with the first leading term not 1. And then you just have to fill in the signs so that you can get a negative 2x when you do the inside and outside terms. And in order to accomplish that, you're going to get this. If you set both equal to 0, you're going to get x is equal to negative 1/3 and x is equal to 1. Okay, so the only thing left to do is to identify if both are the right answer. If not, then we have to sort of go back to the drawing board. So what do we got going on here? If you look at the graph, it appears that we only have one answer. It's right here. So what answer is that going to be? It's going to be all the values that are actually in this interval right here, -1 to 1, but it can't include -1 and 1, and that is the key concept. So this is going to be the answer because it's in this interval, but this cannot be the answer because it's not in the interval -1, 1. Okay, so remember, I basically removed the brackets in order for the theorem removes the brackets, so it doesn't include it. But this is Rolle's theorem in a nutshell. I know it took a while to get through it, but most students, once they do a problem or two, it just you fly through it because it's basically only an easy part of previous problems that we did. Okay, so let's try one more problem. It's going to have a little bit of an extra wrinkle to it. So let's say we have the function, this, again, a third degree polynomial, which is shown over on the right. If we apply Rolle's theorem on the interval -2 to 1, find any points where the derivative is 0. Okay, so what are we doing? We're basically going from -2 to 1, which means if we label those points on the graph, we're about here and here. So what we have to do is we have to just check requirements. So continuous. Well, yeah, it looks like if we follow the curve from start to finish, good. Differentiable, I'm just going to write differ, and you can do that if you want. So that's good. Obviously, it's a polynomial, so there can't be any issues with that. And is f of negative 2 equal to f of 1? Okay, so is that true? So if we look at the graph, we can clearly see that all of these are equal to, both of these are 1, which means that it's good. But what would you do? Again, you would just take each one of these values and you would sub it into the original equation, and each time you would get 1 as your result. So what I'm going to do is I'm just going to write this a little bit better. So basically equal to 1. Okay. So once you know that these are good, then you can apply Rolle's theorem and you're cleared to do that. So what do? You find your derivative, which is going to be 3x squared plus 4x minus 1. And then likely what you're going to do is you're going to set it equal to 0. And then you're probably going to start to factor, right? So you're going to be like, all right, 3x. This is similar to the last problem, actually. One very easy factoring problem. So then you go, all right, well, these two signs have to be a plus and a minus to get this to be negative. So we already know that if it was plus 1 and minus 1, that it's going to be a minus 2x. So what if I did the other one, minus and plus? What do I get? Looks like I get positive 3x and negative x. I get 2x. Okay, we have a problem. So it appears in this scenario that this cannot be factored. Okay, so here's the wrinkle. So this is a problem that cannot be factored. So we have to go back to old school algebra. How do you find the values of x or solve for the true values of x in a polynomial or mostly a trinomial we want to stick to if it's not factorable? Well, hopefully you can dust off the cobwebs and remember we actually have to do the quadratic formula. Okay, yes, that old school formula. So let's, as a reminder, what is the quadratic formula? It's x equals negative b plus or minus the square root of b squared minus 4ac over 2a. Okay, so we have to sub in the numbers. So we got negative 4 plus or minus the square root of 4 squared minus 4 times 3 times, remember the sign, negative 1, right, over 2 times a, which is 3. So if we do the math here, we're going to get negative 4 plus or minus root 28 over 6. And we can simplify this. We might as well just do that as practice. So this is negative 4 plus or minus 2 root 7, because the square root of 4 pops out, over 6, which can simplify it even more to negative 2 plus or minus root 7 over 3. So these are actually the exact values of x. But since we have a graph, we probably want to see what the decimal values are going to be for that. So if you sub this into the calculator, you're going to get x is approximately negative 1.55 and x is approximately 0.22. Okay, so if you look on the graph, you can kind of get an idea of where this is all coming together. So according to this, we started again at this point and we ended at this point, right? So it says there's at least one point where we're going to have a derivative of 0 or a slope of a tangent line of 0. So most students are going to be like, oh, well, this is easy. It's at the maximum. We have a minimum. So that means that if we're trying to locate those values, let me get blue here, then that's going to occur someplace over here, and it's going to occur someplace over here, let's say, just as or for argument's sake. So if you look at the picture, look at our answers that we got here. So you have negative 1.55, which is clearly here, and we have 0.22, which is clearly here. So the key is are these both answers? Or are they both in the interval, etc.? That's the question you have to ask at the end. Well, remember our interval does go from negative 2 to 1, specifically from -2 to 1, remember not including the endpoints. So both of these definitely do that, which means these are the solutions, also can be written like this. So this problem was interesting because this included two results that forced this to happen, and if you think about it, we could get a bunch of results for this scenario if we were to do it in a problem, if you continue on with the concept of this one. So basically, in a nutshell, these are the values of x in which this curve will have a horizontal tangent line where the derivative is 0. Okay, so we learn Rolle's theorem as a way to basically derive one of the most important theorems in calculus called the mean value theorem. This one is sort of similar to Rolle's theorem, but it's more involved, and there's a little bit more you need a little bit more understanding to it. So for the mean value theorem, basically the requirements are almost similar. So we do have a function that has to be continuous and differentiable on the respective intervals, where open and closed, or closed and open, other way around. They do not have to have the same function values. That's not a part of the mean value theorem. So when you get to the labs and homework, just make sure you're not confusing the two theorems. Some students start doing like f of a equals f of b for the mean value theorem, and that is not what you do at all. That's only for Rolle's theorem. So all that's required is continuous and differentiable. It says there is at least one point in C, so we're going in the same direction here, such that this is true. Okay, in the last problem, we had to set the derivative, which was this, equal to 0. Now it's saying that this is going to be equal to this guy over here on the left side. So this should look very familiar to you. That is actually essentially calculating the slope of the secant line. So let's just briefly remember some of this stuff. So if we return to the original rates of change, recall that this is true. So basically, f of b minus f of a over b minus a represented the slope of the secant line, which, by the way, was the average rate of change, where the derivative we know is the slope of the tangent line and represented the instantaneous rate of change. So also, of course, we knew that the limit of x approaches a, the slope of the secant is the slope of the tangent. Obviously, that's important. So what is this theorem actually saying? This theorem is saying that there must be at least one point on your graph where the slope of the secant line is equal to the slope of the tangent line. Okay, so normally when I say that verbally, it doesn't have enough emphasis unless you actually see the diagram to understand what it's doing and how this is actually working. Okay, so starting here, it says the mean value theorem simply states that at some point in the continuous and differential interval a to b, the instantaneous rate of change is equal to the average rate of change in the interval. So as you can see from the diagram to the right, since rates of changes are derivatives and therefore slopes, the lines must be parallel if they have the same slope. Okay, so the idea here is, what's the whole entire theorem about? So let's break this down. So let me get a color going here. So let's say I have 2 points, okay, and I draw a secant line through those points. Okay, so those points are the endpoints of the interval that we're actually talking about. So they tell you the interval, and you use those interval values to draw a secant line through them. What they're saying is, somewhere on this interval, there must be a tangent line to the curve that is parallel to the secant line that you drew. Okay, that is the key concept here. And if they're parallel, that means they have the same slope, which is essentially what this is saying. So if you find the slope of the secant and the slope of the tangent. They are equal to one another. So that is what the mean value theorem actually states. If you have an interval from a to b, if you draw a secant line through those function values of a and b, then there must be somewhere in that interval where there is a tangent line which has the same slope and is therefore parallel to that line. Okay, so that is the technical version, right? But let's talk about speeds. Okay, so you guys remember the trip down the parkway at the beginning of the semester, which wasn't too long ago given this is summer, but if you remember that problem, there was two types of speeds. There was the average velocity, which, you know, what was your average velocity all the way up and down the parkway between the two stops. But there's also instantaneous velocity, which is at any one moment, what was your speed by looking at the speedometer. So what is this theorem basically saying? This theorem is stating that if, let's say, your average velocity, let me write this out, your average velocity on your trip is, let's say, 67 miles per hour, then somewhere on that trip, wow, I can't spell, that's all right. Then somewhere on that strip, your instantaneous velocity also had to be 67 miles per hour. Now think about that for a second. So if you average 67 miles per hour while you're driving, doesn't that mean at some point you had to be going 67 miles per hour at any given time? You probably did that many times, but you had to do that at least once. If you really think about that, then you know that that is absolutely true. And that is what this theorem is actually saying, believe it or not, which is the basis for the mean value theorem. So in order to sort of conquer this type of problem, what I did was I gave you a checklist of things to do. The other problem really didn't need that. It was really easy to follow, but this one can be a little tricky. Sometimes students forget how to do this. So what's the first thing you do in any mean value theorem problem? You find the slope of the secant line. Okay. How can you do that? Very easily, because you are basically, they give you the interval and they give you the function, which means all you have to do is from earlier in the semester, you just find the slope of the secant line, which is f of b minus f of a over b minus a. Now note, this is going to be some constant, right? It's going to be an integer value or a number. It might not be an integer, actually. It could be decimal. But it's going to be some number that you can actually get. What's next? Then you want to find the slope of the tangent line. Now note, the tangent line, the function, is going to be some equation, which means this guy, when you find it, is going to be an equation. Okay, so right now, what is the last step? The last step is the theorem. So it's this right here, this guy. So once you find this, which is a number, and this, which is an equation, what do you do with them? You set them equal to one another. And that is essentially what the last step talks about, is you set them equal and you solve for the remaining. So in Rolle's theorem, you just set the derivative, this guy, equal to 0 because you wanted a horizontal tangent line. Now you have the slope of the secant, so now you have to set the derivative equal to that number to find out where else the tangent line could be that slope. So that is the structure of the mean value theorem. Hopefully that explanation was helpful. But now it's time to do some examples to make sure that all is good with understanding this. Okay, so it says, given the function x squared minus 5x plus 7, find all values that satisfy the conditions of the mean value theorem, by the way, often abbreviated MVT, on the interval -1 to 3. Okay, so again, you're not going to get the picture, which means you need to be able to do this without the picture. But I provide the picture because it's really important for you to see what you're actually trying to find. So, here's the first thing. We are on the interval -1 to 3. So we're basically going from, so -1 is right here, right? We're going from -1 to 3, which is about right here. This is our interval. So on our graph, what does that look like? That's this point and this point. Okay, so note what was drawn here. So for your interval, for your endpoints, you mark them on your graph. So note this is a quadratic function, or a parabola, which you see on the graph, parabola. So you draw a secant line through those points. So here's your secant line. Okay, that's how the mean value theorem starts. You find those points and you draw a secant line. Okay, so what is the point of the mean value theorem? It's to find at least one tangent line that has the same slope as that secant line. So note, I could go here and draw a tangent line, right? Does that have the same slope as this? No. I could go to here and I could draw a tangent line. Does that have the same slope? It's getting close, but no, it doesn't. I could go, what's another point? Look at that way down here. I could go way down here and draw this tangent line to this between -1 and 3. Is that parallel or have the same slope to the secant? No. So what I'm looking for is that exact line that is parallel to this line, the exact tangent line that is. Now you can see it drawn on the graph, but that's not going to be given to you. We have to find that line using the procedures that are shown in the theorem. That is going to be the key to all of this. So what's the first thing you have to do? You basically have to make sure that our spectrum, our graph is continuous and differentiable throughout, and it is. Okay, we have to check that. So we have a polynomial, which means that is absolutely true. Once that is satisfied for our problem, then we can go ahead and do the steps that are here. So why don't we we'll do some Roman numerals setup like I've been doing in some of the other problems. So what's the first step? We have to find the slope of the secant line. Well, we can do that. So what's the slope of the secant line? How do we find that? We basically do f of 3 minus f of -1 over 3 minus a -1. So all we have to do is take 3 and -1 and plug it into our equation. So this is going to be 9 minus 15 plus 7 and so forth. We're going to get 1 minus 13 over 4 when we do that, which is going to give us -3. So just to be clear, the slope of this secant line is -3. Okay. Step 2. We must find the derivative of our function. So again, here, we have to find the slope of the tangent line. So that's going to be, if you look at it up here, that's going to be 2x minus 5. Okay, so as I promised, remember what I said up here? So this is going to be a constant. What do we get? -3. This is going to be an equation. What do we get? 2x minus 5. So hopefully everybody sees that. I'm trying to be as specific as possible so it makes life easier for you. So what do we need to do in the third step? We need to find where, you ready? I'm going to write it as I say it. Where the slope of the tangent line is equal to the slope of the secant line. Tangent slope, secant slope. Okay, so we solve this. We get 2x is 2 and x is 1. Therefore, it says find all values that satisfy the conditions. It should say find all values of x, but that is basically the answer to the problem. And if you look at the graph, if I plug 1 in to this right here, I'm going to get 3. So that creates this coordinate here, which I plotted on my Desmos. Actually, this is from Desmos. So on my graphing software, I actually plotted that equation on the line, and you can see that they are perfectly parallel to one another, and they have the same slope. So this was the point of it. So again, you're not going to get this picture, but the picture is really helpful for you to understand why you're doing what you're doing, because you're more likely to look at this stuff and not forget it. You're more likely to be, oh, this is the one where I need this slope to be equal to this slope. So now I just got to find them. So as long as you understand what you're doing, it makes it easier when you're doing the problems, obviously. Okay, so let's do another problem. So as I usually do here, I'm going to pick up the skill level as we go because I want you to get a nice sort of broad look at examples that might involve special rules or maybe trig or logs or something that's going to be a little bit different sort of feel on it so it's not too repetitive. So again, what we have here is we have it looks like a rational function, x squared minus 9 over 3x, and we need to satisfy the conditions on 1 to 4. So what are we looking at? So we're going from 1 to 4, which gives us the following points. This guy here and this guy here. So it says there exists some, basically what do? We draw a secant line through, so the blue dashed line is the secant line. So this is saying there exists at least one point of x, value of x, on this line where there's going to be a tangent line with the same slope as the secant. In other words, these are parallel, right? That's it. So yes, it's all out in front of you as the answer here. We already have it, but you're not going to be given this, so let's figure it out as if we weren't given the picture. So again, this is continuous and differentiable throughout. Okay, so that's good. So then let's go right to our process. So what do we need to do? The first thing we always do is find the slope of the secant. So it's f of 4 minus f of 1 over 4 minus 1. So we just have to make sure to plug in 4 and 1 into our function for x and then find those values. It's going to get really ugly because these are fractions that you're going to get. So you're going to get 7/12 minus a negative 8/3 over 3, which if we do the math, I know most of you are just going to go into your scientific calculators and use the fraction buttons and everything in order to do this. But let's say we didn't have that and we did common denominators. We would get this, and then when we divided, we would get this, and then we would get this. So basically, the slope of the secant line, which is here, this slope is positive 13/12. Next, we have to find the derivative of our function, but hopefully there's warning lights going on here with this derivative. This requires the quotient rule. Okay, so we need the quotient rule in order to get this. We also, by the way, don't have any constants alone anywhere in the numerator or denominator, so we can't adjust this to make this easier. We literally must do the quotient rule. So what does that look like? So we're going to do the derivative of x squared minus 9 times our denominator 3x minus x squared minus 9 again times the derivative of 3x all over 3x squared. Quantity squared. All right, so if we keep on going here, looks like we're going to get, if we want to do a little shortcut, so this is 2x, this is 3, okay? So what does that look like from here? So we're going to get 2x times 3x, which is 6x squared. We're going to have this 3 right here has to distribute as a negative to x squared minus 9. So we're going to get negative 3x squared plus 27 all over 9x squared, which is our denominator. Now, note here that we can collect like terms and get positive 3x squared plus 27 over 9x squared. And we can go even further because each one of these is divisible by 3, so we can get x squared plus 9 over 3x squared. Note, if for some reason, like this 27 was a 26, we would not be able to simplify that whatsoever. So only because all of the quantities are divisible by 3. So basically, so far we have this and we have this. So this is the slope of the secant. This is the slope of the tangent. In our final step, what is the point of this? It's setting those two equal to one another. So that is exactly what I'm going to do. And we have just pure awfulness that we're looking at. So there's a couple ways that you could do this. If you're going by the strict, like, more advanced algebra way, what would we do? We would multiply both sides by the least common denominator. Well, the least common denominator is 12x squared, so we could do that if we wanted to, but this is also a proportion, which means we could cross multiply to get the desired result. It really doesn't matter which way you do it. I just, for argument's sake, let's just say we cross multiplied. We would get 12 times x squared plus 9 equals 13 times 3x squared, which would give us 12x squared plus 108. I think that's 108. 9 times 2, yep. And that's 39x squared. Again, we want to collect like terms. Get the 12 over, get 27x squared. Move up here, get x squared is equal to, believe it or not, looks like 108 divided by 27 is 4. So what do we get as our results? And be careful here, plus or minus 2 when we take the square root of both sides. Okay, so the key step in the end here is, in this problem, this value here, which maybe I didn't mention that, but which I should have, but this value here is in this interval, so we're good, right? It works. So if you look at -2 and 2, we have to verify that these are basically, let me do a different color so it sticks out. We have to verify that this is actually in our interval. So it appears that x equals 2 is an answer, but note that x equals -2 is not in our interval, which means it is not an answer to our problem. Okay, which means our only solution is x equals 2. So well, let's look at the graph. Look, I plugged 2 into the original equation, got the actual point here, and this point is where we have a tangent line, which is parallel to the secant line, or in other words, has the same slope. So that's another mean value example. Let's try one here for 4, our last one. Number 4, it says, given f of x equals 2e to the x, find the values on the MVT on the interval 0 to the natural log of 3. Okay. So obviously trying to play around with things that might make students uncomfortable when it comes to mathematics. E's, natural logs, basically non-polynomials, non-rationals, just to make sure all is good with that. So the first thing we have to do is determine continuity and differentiability. So maybe this might be a struggle for some students, because they'll be like, well, if I see I didn't, all these I included the graph, but this time I didn't. I did it on purpose, because no graph means, how do I figure this out? How do I determine this? Well, first things first, an exponential function's domain is all real numbers. So this is something that students should know, but I have a feeling that that's not exactly something that's sort of hanging around in the brain, so to speak. So I just want to show you what it looks like, so all is good. So I have this cool calculator simulator for the TI-84 Plus that anybody can download for free, by the way. It's called CEMU. Basically what you can do, I'll show you what it is. So I'm going to go into y equals, and I'm going to put in 2e to the x. Alright, and then I'm just going to do zoom standard, and this is my graph. So if you look at so this is basically the same functionality as your calculator. So if you look at the graph, basically the range is limited. It can only go above 0, all positive numbers. But the value over that, even though it looks like it's going straight up the graph, it goes on forever, which means we don't have any problems with continuity or differentiability. We're good to go when it comes to figuring out the mean value theorem. So continuity and differentiability is good. Alright, so what else? What do we go do next? So we have to do f of natural log of 3. I know, so all of a sudden things are getting a little crazy here. Minus 0 over the natural log of 3 minus 0. Okay, so that's different, obviously. Much different. But we need to use natural log of 3. And no, you do not want to use your calculator for this. We want to use exact values. So stay away from the decimal stuff. When it comes to this, I'm purposely giving it to you so that you don't do that, because I want you to remember log rules. So if we plug in these values, what are we going to get? We're going to get 2e to the natural log of 3 minus 2e to the 0. So all we're doing is plugging in for x. And then on the denominator, we're just going to get natural log of 3. Okay, if we do the math here, remember e to the 0 is 1, so we know that this right here is 2, right? But just a shortcut, it's a famous, basically, let me get rid of this arrow. E to the natural log of x is actually equal to x. So whatever this value is right here is always going to be this value. So that means e to the natural log of 3 is just 3. So we're going to get 2 times 3 minus 2 times 1 over the natural log of 3, which is going to give you 4 over the natural log of 3. So this right here is the slope of the secant line. Do not use decimals if you want to be exact. And we do that most of the time. The only time we use decimals is for when we want to approximate looking at a graph or we have an application problem. Okay, so we also have to find the derivative, our second step, because we need the slope of the tangent line. So what's the derivative of 2e to the x? Well, constant goes, just the constant multiple goes along for the ride. Derivative of e to the x is e to the x. So not much actually was accomplished with that. That's just the easy, simple derivative. So the last step is to set these equal to each other, and what do we get? We get something that is quite horrific looking. So this is the equation we're going to have to solve. Okay, we have to return to pre-calculus. If you were at a university, just pre-calculus. If you were at a county community college, then you probably took it in 2 parts, so pre-calc 1. What do we do? Well, basically, if we want to solve for x, we need to isolate e to the x. So we need to get that 2 out of there. So we divide both sides by 2. Remember, when you divide by 2, it's the same as multiplying both sides by a half. And if you multiply this by a half and simplify, you're going to get 2 over the natural log of 3. So just to be clear, if we did, and as an aside, 4 over the natural log of 3 divided by 2, that's going to be equal to 4 natural log of 3 times 1/2. And if you simplify that, you're going to get that, which is 2 over the natural log of 3. Okay, so once we're at this step, this is the key concept. So how do you solve an exponential? The only way to solve an exponential, specifically e, is to take the natural log of both sides. So what I'm going to do, actually, you know what? I'm going to do that in the next step so that it's a little bit clearer. Undo out of here. All right, so in the next step, I'm going to take the natural log of e to the x, right? And again, the natural log of 2 over the natural log of 3. Okay, that's my next step. And note again, this is another shortcut. If you do the natural log of e to the x, that's always equal to x as well. So these are two, basically they're called log identities. So they're true no matter what, and this one's really easy to prove because if you, in a log, you can move this to the front. So you get x natural log of e, and natural log of e is 1. So you just get x. So if you get this as your result, what do you basically this whole thing is x. So that means the answer to the problem is natural log of 2 divided by the natural log of 3. So believe it or not, this is the answer to our problem. Now note though, you have to evaluate this to make sure that it's actually in the interval. Okay, so if you plug in, so for example, just to be clear, because we don't have this, so actually I don't need that whole thing there. So the natural log of 3 is actually equal to 1.0986 approximately. Okay, and then this value is approximately 0.5991, right? So that means that this is comfortably in your, let me change the color, this is comfortably in your interval right here, which means this is definitely the solution to the problem, the exact solution. And in most standpoints, that's what I'm looking for, is the exact solution. I know in some problems we ended up with like a decimal result. I don't know, I think it was maybe not these, but maybe in Rolle's theorem. We ended up with a decimal result, but I'm usually looking for the exact because that is the calculus way. All right, so this is all about the mean value theorem's 2 requirements, continuity and differentiability. So this is how we finish. I just want to make sure everybody clearly understands when the mean value theorem cannot be applied, because clearly in all the examples we did, in order to accomplish what we were doing, it had to actually satisfy the requirements, which we showed, But what happens when it doesn't? So look at number 5. It says, let's say we graph tangent. So this is the graph of the very popular base trig function tangent, but we're on the interval pi over 4 to 5 pi over 4. So if we go and label the points on the tangent graph at those values, what is the issue? Okay, when you look at this. So why would this not be an example of being able to apply the mean value theorem? Well, you can clearly see that there is a vertical asymptote right here, which means this breaks continuity. So basically this will not work because this is not continuous. Cannot apply the mean value theorem because this is not continuous at x equals what? Okay, well, it looks like pi over 2 is where our asymptote is, and if you remember from trig, that's where it always is for the base tangent function. Now, if you look at 6, what about x to the 2/3? Okay, so this is like the seagull looking. So if I was to draw a seagull, I would do that. So this is the seagull. It's a cusp, right? So if I'm on the interval -1 to 1, which means I go to my graph here, okay, why is it that I cannot use the mean value theorem? Well, if this is a cusp, that means that this is not differentiable at x equals, it looks like 0 is where our problem is, where our cusp is. So we don't get this very often. I mean, it definitely could happen here. I mean, this is a basic graph, right? But it's very important that you understand that there are scenarios where you absolutely cannot use the mean value theorem, just like there are scenarios when you can't use Rolle's theorem. So this does come up in labs, FYI. It could come up in the homework too. So just make sure you're prepared to just don't jump right into the problem. Always check conditions, even though they might not seem important, they very much are.